Dear students, today we will be continuing with the next topic of process concept, that is process states. In this, we will be discussing about process state diagram followed by process control block and what all happens when the CPU switches from one process to the another. So let's continue with the process state diagram. So if you see over here, basically a process can be in any one of the 5 states during its lifetime. That is from process creation to process completion. So these 5 states are new, ready, running, waiting, and termination. As far as the first state is concerned, that is new. So it is that state which is where when the process has been created, that is, it is the newborn state of that process. So once the process has been created, then there are certain possibilities that what will this process do thereafter. So obviously the process is supposed to do some task. So for that process is shifted from this place, that is the new state, onto the ready state. It is placed over here. This means this process is now in the main memory and is waiting for CPU's allocation so that this process can start its working. So the question arises whether this process, which is right now residing at this place, will it immediately get the CPU so that it can begin its execution, or it has to wait for some point of time so that it can start its execution. It all depends upon like if this is the only process which is in this ready state, and simultaneously at that time the CPU is also idle. In that scenario, this process will be immediately be given to the CPU so that it can start its execution. That means this process is shifted from ready state onto the running state. When a process is in the running state, that means that process has gained the access of CPU and is now executing. So as I've told you, it all depends upon whether this was the only process in the ready state and CPU was also idle. In that case, it is immediately transferred from ready state onto the running state and that process is executing. But what if there are number of other processes which are there in the ready queue? Let's suppose P1, P2, P3 are already over there, and then this P4 is also, and P4 has also entered into the ready queue. So in that scenario, and at the same time, the CPU was working on some other process. So that means these 4 processes are waiting for their turn to get the allocation of CPU. So the moment the CPU is free, that means running state as of now is not having any process. In that case, one of the process from this ready queue is shifted to the I would say to the running state. Fine. So the question arises which one of these will be shifted from ready queue onto the running state. So I'm using two terms over here, vice versa, I would say, or I would say, sorry, not a vice versa, I would say interchangeably. One is ready queue, or I'm using the word ready state. I'm referring to same thing. Why I'm using the word queue? Because all the processes which are waiting for their turn for the allocation of CPU are basically placed in the ready state. So a queue is maintained over there. Likewise this, where I'm assuming that P1 was the first one who entered the ready queue, then comes P2, then comes P3, and later on P4 also entered into the ready queue. So let's assume that the CPU allocation is given to these processes in the order in which they arrived. That means P1 arrived first, then P2, then P3, then P4. So P1 will be getting the access of CPU immediately once the CPU is free. So this process now shifts from this place onto the ready state, and I'm saying that ready state is to the running state. That means now the CPU will work on process P1. Fine. So once that is going on, that means now P1 is not the part of ready queue as of now, because P1 is executing now. So P1 is over here. Now the question arises, what happens when this process is, after this process has executed? Now there are two possibilities with regard to the process which was with CPU. And those two possibilities are that either process P1 has completed its task. Suppose it has completed its task. That means process P1 will move on to the termination state. That is the last state. Whatever task was given to the process P1 for its execution, that task is complete now. So automatically the process P1 moves into termination state and is not the part of system now, because it has done its job. But let's suppose that another scenario over there. That scenario is, in case P1 execution is not over, but it needs to have access of some input or output activity. So in that case, what will happen? This process P1 will now be shifted onto the waiting queue. Why waiting? Because its job is not complete as of now, but it needs to perform some input output activity, and once that activity is done, then again it needs CPU's access to do its remaining job, and thereafter if it completes its task this time, it will move on to the termination state. So fine. So what I'm assuming over here is that P1 has not yet completed its job. So and it needs some IO or some event to happen. In that case, this process is shifted from running state onto the waiting state. So in the meantime, again CPU is idle. So the next process which was in the queue, that is P2, this will be shifted on from ready queue onto the running queue. So CPU is busy with now P2, and P1 is in the waiting state. Now at this juncture, I would say P1 was waiting for some IO activity, and let's suppose that IO activity is complete, that is done. So again this P1 is brought into the ready queue at the end of the queue, because it again now needs CPU to do its remaining execution. So again this P1 will get its turn once the processes which are waiting before this P1, they complete their job. This will again gain the access of the CPU, and suppose this time it has done its job completely. Whatever the job was allocated to P1, that job is now done. So in that case, P1 now will be shifted on to the termination state. So likewise, things are taking place over here. That is, movement of the process takes place from one state onto the another. Now there is one more term over here, and that term was scheduler dispatch. Basically, as far as scheduler dispatch is concerned, it is the responsibility of the operating system who actually schedules the processes for execution. So we will study this thing in the coming part, in the next topic, where I'll explain the concept of scheduler over here. We do have a long-term scheduler, we do have medium-term scheduler, as well as we do have short-term scheduler. So we'll be reading this thing, we will be learning about this thing in the coming I would say topic, when we'll be discussing that part. So let's move to the next part now. I hope you have got the idea of how a process is shifting from one state to another state, and once the process is born, and how its execution takes place, and finally it moves on to the termination state. So this is the entire diagram which depicts the various states with regard to the process transition. So let's move to next topic now, that is process control block. Now as far as process control block is concerned, if you see, we need to remember one thing which we have read so far. As I've told you earlier, about process P1, which was earlier it got the CPU's time for execution. So it executed for some time, and in between it needed some IO. So this process was IO activity. So this process was shifted from running state onto waiting state. So earlier it was running, but now it was waiting. So before it moves to waiting state, suppose we are saying this process was supposed to do some work. Suppose this is the task which it was supposed to do. So once it was with CPU, this much amount of task was done. And this is the pending task which is yet to be done. And the process has shifted from running state onto this waiting state. Fine. And then whatever activity was to be done in the waiting state with regard to IO, that activity has completed now. We are assuming that that activity is complete now. Now this process P1 again enters into the ready state and is again waiting for its turn to get allocation of CPU, that is to move from ready state onto the running state. Fine. So let's suppose that again it got the access of CPU. Now the question arises, will it again restart its job from this place, or will it continue from the place from where it left? So yes, it will continue from the place from where it left. That means the task which it has done priorly, that task is fine, but it needs to continue with the remaining part now. Fine. A question arises, how come this time the CPU knows that how much task was done priorly and how much part is pending, so for that your process control block, that is PCB, fine, also called task control block, this is something which comes to the assistance of the CPU. So I would say that every process has its unique process control block. For every process, the set of things which are stored in the process control block are process state, program counter, CPU registers, scheduling information of CPU, memory management, accounting information, and IO status information. That means whatever information is there with regard to the process, the entire information is stored in this process control block. So every moment, whatever state change takes place within the process, that activity is recorded in this process control block. Let's suppose that the process executed for the first time, it got the access of CPU. Let's suppose for, I am assuming that the time is 3 seconds. In fact, it is a very big time. Actually, it is in milliseconds only, but let's take something which I can explain in a better way. So I'm assuming that for the first time, it executed for 3 milliseconds, or let's say 3 seconds. Fine. So every second when the execution was going on, that is in first second, in second, and in third second, the state of the process was changing. So some values were changing during its, when some calculations were going on, the entire set of things were changing. This PCB was updated every moment whenever there was a change. For example, if we see the things which are mentioned over here, the very first thing is process state. It specifies that as of now, what is the state of that process. It can be in a newborn state, it can be in a ready state, it can be in a running state, it can be in a waiting state, or it is halted, and so on. That information is stored in this part of the process control block. Then the second part is the process number. The process number specifies an ID. Each process is having its unique ID. So that ID is allocated the moment the process is born. So as number of processes are over there in the system, so to keep track of each of the processes in a unique way, an ID is allocated. That ID is stored, or which is referred to as a process number. Then the next information is the process program counter. This counter basically contains the address of the next instruction which will be executing after the current instruction. we have read this thing about the working or what the purpose of program counter in our previous video. I've explained you over there. So program counter indicates the address of the next instruction to be executed after the current instruction for this process. Fine. Then the next thing is about CPU registers. As far as CPU registers are concerned, the number of CPU registers and their type, it all depends upon the architecture of the computer on which we are working. How many registers are there and what is their type, it depends upon the architecture of the machine on which we are working. As far as type of registers is concerned, it includes accumulator, it includes index register, it includes stack pointers, it includes general purpose registers. So basically, for example, if I take the case of accumulator, so basically if some mathematical calculations are going on over there, the values are stored in accumulator or some general purpose registers. What memory is being allocated, so likewise some information with regard to the addresses is also stored. So for example, if I talk of the next part, that is the memory management information. So as far as memory management is concerned, I would say that it includes the values of base register as well as the value of the limit register. So because in the memory, number of processes are allocated space. So for a particular process, so which area of the memory is allocated, from where which address it begins and till which address it continues. For example, I am saying that, let's suppose in a layman's language, let's suppose location from location number 400 till next 35 locations, let's say. So the base register basically will hold the beginning address of the process, that is 400, and the limit specifies the next number of locations. If they are 35, that means beginning from 45 for 400 till 435, next 35 locations are reserved for the process which this process control block is about. If this process control block is about process P1, so the memory allocations, the base specifies the beginning address and limit specifies the corresponding number of locations which are reserved for this process P1 with regard to its working. Fine. The next thing over here is the CPU scheduling information. For example, it includes information regarding what priority this process is having. So question is, what is this priority? So if you just recall the previous slide, I told you that suppose in the ready queue, P1 was the first process which was waiting, then P2 was in the ready queue, P1 was in the ready queue, then followed by P1 was P2, then P3 and then P4. So if all the processes are of same priority, in that case, the one which is at the start of the queue, it will gain the access of CPU first, later on the next one, then the third one, then the fourth one, because all of them were of same priority. But what if there is a process which is having a higher priority as compared to the other processes which were over there already waiting in the ready queue? So it all depends upon what kind of task it is. Let's suppose that activity, some interrupt has occurred over there and it is some inbuilt system related task which is having higher priority. So in that case, if a process comes in the ready queue which is of higher priority, in that case it will basically bypass, if we assume that process P4 was of the highest priority, in that case these processes will not get the turn first before P4, but P4 will gain the access of CPU rather than P1, P2 and P3. Why so? Because P4 was of higher priority over there. So that information is also stored within the process control block. Apart from that, then there is scheduling queues. Scheduling queues, queue pointers, basically we'll be covering this thing in the, I'll show you in the next slide that how this information is helpful in terms of execution. Apart from this, the another thing which is stored in this PCB is about the accounting information. It specifies the information like amount of CPU time which is used for execution of the process, and what is the maximum time that this process will get from the CPU for its completion of execution. Similarly, the process numbers. So such things are basically stored in the accounting information part of the process control block. Thereafter, the last thing is IO status information. It basically specifies that the list of IO devices, as I've told you in the previous video, a process needs certain resources for its execution, and these resources includes maybe some input as well as some output devices. So this part basically specifies that which devices as of now are already acquired by the process for its execution. Plus, it also specifies what are the various files which this process has opened to do its execution. So all such things, the information about all such things are basically available in the IO status information. So as I told you earlier, this process control block keeps up-to-date information about the process during its execution. The moment the process has been terminated, this process control block for that process no more exists. But in case it switches from running state onto the, I would say, waiting state, this PCB is stored. Why it is stored? So when this process again gains the access of the CPU, the saved state is brought into picture so that the CPU can begin from the place from where it left and can complete the remaining execution for this process. So when now there's one more scenario. When an interrupt occurs, the information available with the PCB must be saved. For example, I've told you, suppose process P0 was as of now executing, and P1, P2 and P3 were in the waiting state. P0 was executing, that means it was with CPU. So all of a sudden process P4 came, and this process was of the highest priority. In that case, P0's P0 has to immediately leave the control of the CPU, and so that P4 can take the control of CPU for its execution. Now question arises, because P0 was executing, whatever values were held in the PCB for P0, some values were in this area of the I would say the process, in this area of the process control block, that state is saved now. Why it is saved now? Because P0 has yet not been completed. It was stopped in between because a higher priority process came and it was given allocation of CPU. So this P0 switches from running state onto the ready state. If you remember about the previous diagram, earlier there was a scenario that the process stopped working because some IO activity was to take place first. In that case, the process shifted from running state onto the waiting state. But in this scenario, this process was already running and no such IO activity was required by this process for its execution. But what happened? Because the new processes came and that was of higher priority, and this process has to leave the control for that process, the high priority process, to start its execution. So in that case, it doesn't move on to waiting state now, but directly from running state onto the ready state. Fine. And in the meantime, before that shifting is being done, before that switching is being done, the state of the process control block for process which is right now shifted from running to ready state, that state is saved somewhere. Fine. so that later on when this process again comes for execution, the PCB for that process can be handed over, can be passed on to the CPU so that it can start with the remaining task. Fine. So let's now move on to the next slide. So if you observe over here, I'm showing you two processes, that is process P0 and process P1. Fine. Now if you observe over here, as of this is the timeline, this part specifies the timeline. Fine. So let's suppose let's suppose 0 to n units at time t0, that is at this time, which is executing, it is process P0 which is executing. And what is P1 doing at that point in time? It is doing nothing. As of now, it is waiting. It is in the ready queue and is waiting for its turn to get the access of CPU. But as of now, process P0 was having the access of CPU. So what happens over here is, all of a sudden an interrupt occurred or a system call occurred, and that system call was having higher priority as compared to the process P0. So this means what? Process P0 has to leave the control of CPU so that process P1, which because of which the interrupt had occurred, can take the control of CPU. But before the control can be transferred to P1, if you see over here, we are saving the state of PCB for process P0 because it executed for only a small amount of time. It has not yet completed its task, but because an interrupt has occurred due to which this process has to leave the control of CPU, so before it leaves the control of CPU, its state is saved, that is PCB0 of process P0 is saved. Then who is to come now for execution? It was process P1. So before process P1 comes into picture for execution, first of all we need to reload the state of process PCB. We need to reload the state of for process P1, the PCB for process P1, so that now the CPU can start working on with regard to process P1. As I've told you, for both, in this case we are having only two processes, so we are having two PCBs, that is PCB0 and PCB1. Even if the process is coming for execution for the first time, still the set of values with regard to that process are already over there in the PCB. Fine. So if you see over here, we are before a process can start its execution, that is, when I'm saying start its execution, I mean to say allocation of CPU to that process. So before a process P1 can start its execution, first of all the PCB of that P1 needs to be loaded. Fine. So that it can begin its so that CPU can work on that process. So once, if you see over here, once the process once PCB has been loaded, then P1 is executing, and during this time, if you see, when the state saving was done for process P0, that is PCB0, that is process control block of process P0 was saved, it is now idle, and it remains idle till the time it again gets the access of CPU. So what I'm trying to say over here is, first of all, when the control is transferred or switching is done from one process to another, first of all we need to save the state of already executing process. Then we need to reload the state of the new process which will get the access of CPU. Thereafter, this new process will start its execution. Once again an interrupt occurred and PCB of that executing process is to be saved, because now again I am saying an interrupt has occurred. So that means P0 has to leave the control, P1 has to leave the control now, So who will gain the access of CPU? Let's suppose it is P0. So before the P0 gains the access of CPU now, first of all we need to save the state of the existing executing process, that was P1. Then we need to reload the state of process P0 because it executed for some point of time. So this basically saved state is now reloaded at this time when it again comes for execution. Once the reloading is done, thereafter the execution of process P0 begins. So it all depends on how many. I have quoted an example of only two processes over here. Even if we are having 3, 4, 5 processes, this will remain same for all such cases. That is, the moment CPU is allocated, before that we need to upload the, or we need to reload the state of that process. Only then this process can begin its execution. And then again when somebody else gets the control, so first of all we need to save the state of the currently executing process, then reload the state of the new process which is coming for execution, and thereafter this new process will actually get the access of the CPU. So I hope that you have understood about now the process states as well as how switching is done from one process to another with regard to the CPU. So that's all with regard to this lecture. Thank you.